Welcome everybody to the 1W-MINDS seminar on maybe the last day of summer, or at least getting close. It is our distinct honor today to have Deanna Needell here to speak to us about non-negative matrix factorization and other topics. Professor Needell is the Dunn Family Endowed Chair in Data Theory and the Executive Director of the Institute for Digital Research and Education at UCLA. Her many awards and honors include the IMA Prize for Math and Mathematics and its Applications, the Alfred P. Sloan and NSF Career Award, and she serves as an editor for several journals as well. And instead of going through her incredibly long list of honors, I will instead give her more time to talk, because that should be more interesting. So I'll turn things over to you, Deanna.
Thank you, Mark. Thank you for the invitation and for hosting. So as usual, I would like this to be fairly informal. Folks want to interrupt the people that have the speaking privileges, or in the Q&A, anyone can interrupt me and ask questions or comments. Totally fine as we go along. So I have a few things in here. I have a very brief introduction to MMF. I assume most people probably already know what it is, but just in case. And then I'll talk about some relatively recent work on some theoretical guarantees for an online MMF method, as well as a bunch of applications near the end. So hopefully near the end, if folks are still with us and awake, it'll be mostly pictures. So the bulk of this work is in collaboration with these folks here. So Dr. Han Liu, who has just moved from UCLA to University of Wisconsin, as well as Laura Balzano at Michigan, and my PhD student, Chris Stromer, as well as a bunch of other folks. So we have an RU group from 2 years ago, pre-pandemic. You can see we're all in person there. And then an RU group from last summer here, as well as my research groups, several folks from there. So a combined collaboration with many folks. So non-negative matrix factorization is pretty much as the name suggests. You start with a large data matrix, which I'll kind of envision as users by variables, and we're looking to do a factorization into something that might be users by topics times topics by variables. What does it actually mean? So we're going to typically ask both the data matrix to be non-negative as well as the factors. So typically both factors will be non-negative as well. And so what this means is that large entries will give you some insight into what these topics actually mean. So for example, if this entry here is large relative to the rest, then that signals to me that this user corresponding to this row is highly correlated with whatever this topic represents. And if I want to then understand what this topic represents, I go ahead and look in that corresponding row in this factor. And then I look at the variables that have large entries, and then those variables would be associated with that topic. So as an example, if we're looking at something like users by movie ratings, kind of a quintessential example for topic modeling, then I can interpret these topics as maybe genres of movies. And so if this user has a large entry in this genre topic, and I look at the corresponding variables or movie ratings in this genre topic here, and I might see the large entries correspond to the movies Titanic, Love Actually, Sleepless in Seattle, then it's up to me to interpret what this topic means. And I would probably interpret this genre as maybe being romantic movies. I guess Titanic is not a comedy, as was pointed out to me. So something like this. So it's a little bit subjective, but this is kind of the idea. You go back and forth between these two. So just to throw it out there, right? If you just saw maybe a little bit of something different, you saw these three movies, then I might change my interpretation, right? So the good news about NMF is that because of the non-negativity, we'll see that you really do get interpretability. But of course, like many of these methods, it is still subjective. There are many, many, many variants of NMF. Some relevant to this talk will be a semi-supervised version of NMF. So if I have label information about some of my either users or variables, depending on whether I want to transpose the system or not, then I can consider this like Y matrix, which will be a label matrix for C classes. So the rows here would correspond to the classes that I have labels for. Then I can write down the NMF problem as minimizing both the reconstruction error. So I want the factors A and S to give me a good factorization for the data matrix X. And then I also want the labels to be accounted for. And the lambda parameter, of course, just tunes the balance between these two errors, classification and reconstruction. So more mathematically, the goal of NMF is, as I said, to factorize a data matrix X into a pair of low rank non-negative matrices W and H, or A and S, depending on which notation we use, by solving the optimization problem without the semi-supervision, just minimizing the factorization error, typically in a Frobenius norm. And so the language that we'll use, so this will be the data matrix, which will be D by N, and then we'll call this first factor W the dictionary. So I'll view these columns as dictionary atoms. There will be R of them. And then this H matrix will be the coding matrix. And because we want understandable topics, typically R, of course, is much smaller than both D and N. So an online version of NMF is going to consider data that is streaming in over time, or data that just already has a time series structure. So the goal, well, in this case, will then be to learn a factorization that is best typically in something like expectation. So this means that we're going to assume that the data is coming in according to some distribution, and then I want to learn the W and H dictionary encoding pairs that give me the best error on average. And so this can be used for actually many things, and in particular, we're going to use it for prediction and time series data as well. And to do prediction, what we do is we consider learning these factors across time as we're like sliding a window across all the data matrices, and we update the factors as we go. And if I just extend the window a little bit beyond what I currently have data for, and I make that prediction, then that actually becomes more of a prediction and less of just a factorization. So I'll explain that a little bit more when we get to those applications. All of what I'm saying can be extended to the tensor case. It's a non-trivial extension, but it's everything is analogous. It takes a little bit more work to show some of these updates still work, but indeed they do. But I'll just stick to the matrix case to make the notation a lot easier. So as I said, the reason that non-negativity is important here is strictly for interpretability. And so what we're really asking for is each column of the data matrix to be represented as a non-negative linear combination of the dictionary atoms. And so we can see in this example that this forces a dictionary to be positive parts of the columns of the data matrix. And this allows for interpretability. So kind of a classical example, which was due to Liu Sung in this seminal paper from '99. Shows if I apply an NMF to a database which consists of human faces, then the parts that I learned, so the dictionary atoms, it's kind of hard to see probably because it's so small, but you end up learning dictionary atoms that look like noses, eyes, mouths, and things like this. So actually kind of parts of the face that are interpretable to us humans, versus something like PCA that learns, these eigenfaces that still give good decomposition, obviously, but aren't really meaningful from looking at them. And why is this? Well, because when you allow, of course, negativity, then you're allowing for cancellations. And so while these things still add up to give the face, they don't really have as much meaning. So that's the reason for non-negativity. This was just a fun example that our students did. So they took an Escher image, this original image here, which of course has a lot of geometric structure to it, learned dictionary atoms, which look like this, which again are very kind of hard lined and geometric in nature. And then they use these atoms to reconstruct the original image. So you can think about this as a way of doing compression. It does a pretty good job here. But you can also do something interesting like reconstruct a different image using these same atoms. And so here they reconstructed this Renoir image, which of course is very far from being geometrically structured. And so if you were to zoom in on this, you would see that very close, in very small areas, you still have this like geometric structure, which is counterintuitive to the kind of smooth brush strokes that you would typically see. So kind of some interesting things one can do there. Okay, so going to online NMF, first let's look at what happens in a static NMF. So typically to solve this optimization problem, one uses something like block-Horn descent or multiplicative updates that iteratively fix W or H and then minimize the error with respect to the other. So we can kind of visualize this here where we're fixing W, learning H, fixing H, learning W, and so on and so forth. But the data matrix X here stays the same throughout. So this is static. Using this idea, you get the most popular NMF method called multiplicative updates by these same folks. And this kind of process just leads to something very straightforward, very easy to code, which actually just updates these entries according to this simple, as the name suggests, multiplicative update rule. So we can do something similar in the online case. So the error of this, using this multiplicative update rule is known to be non-increasing, but there is no guarantee to converge to a stationary point. So what changes if we're now assuming instead of having just a single matrix X, if our data is actually changing over time? So for example, if X is randomly drawn from some sample space according to some distribution pi, can we still learn the best dictionaries again in expectation? This leads to the online non-negative matrix factorization problem, so 1MF. And again, everything looks kind of the same, but the data, of course, is changing. So that's the key here. So we have these iterates, but we can imagine kind of doing a similar thing where we're still iterating between W and H, but now our actual underlining data matrix is changing as well. So it will be indexed by T. So here's one thing we would like to look at. If this data time series XT is an irreducible Markov chain on a sample space omega with the unique stationary measure pi, then our goal of ONMF would be to construct a sequence WT and HT, again, of the dictionary encoding pair W and H, such that almost surely we get that the error at time T with respect to the factorization at time T, W and H, that error converges to the best in terms of the factors W and H, error in expectation, where the expectation is taken over the randomness in the data X. So this is the best factorization in expectation, and we would like to see this convergence over time. Okay, so to get a little bit more specific into some of our convergence guarantees, we're actually going to address the most common, or one of the most common loss functions, which is a quadratic loss function with an L1 regularizer. And so for some lambda, we'll define this loss L, which is a function of both the data and one of the factors W, which measures, again, this factorization error in Frobenius norm, plus an L1 norm over H. And so there's a couple of reasons one might want to induce something like sparsity in H. Typically that is for interpretability. Also, there's some computational reasons why that might be advantageous. But if you have too many variables in your topics, then it's again hard to interpret, right? So you want non-negativity as well as sparsity really aids in the interpretability. So that's why this regularizer sort of makes sense. And then we'll define the expected loss. So just the expected value over the data of this loss function, I'll call that F of W. And the average empirical loss, I'll call FT of W. So at time T, we just take the average over all of the losses that we've seen. So these will be important in building the algorithm. So a couple of things you sort of get for free by the Markov chain ergodic theorem for each dictionary W. The empirical loss, FT of W converges almost surely to the expected loss. That was weird. Everybody disappeared for a second. Okay, but looks like we're still here. So you get this convergence almost surely. And so a naive solution to solving Ontf based on this kind of block optimization scheme would be something like this. So upon arrival of a new data point xt, you might update ht by simply minimizing overall such non-negative h's, the loss function, right, at time t. And then you might update w by minimizing this empirical loss. This would be things that you actually have your hands on that you could do. Where I'm now minimizing over maybe a set of admissible dictionaries, which could just be non-negative, for example. A couple of issues. One, this requires you to store all the previous matrices from the history of time, right, since the very beginning, since you're using this empirical loss, as well as solving many optimization instances. So both of these are kind of reasons why this might not be computationally practical. And so there was a solution to this given by these folks here, Mile, Bach, and Sapiro. Gave a solution to this with a rigorous derivation of almost sure convergence of the empirical loss, but they studied this for IID data matrices. So this is what they did. They adjusted something ever so slightly. So this setup here looks identical to the one on the previous slide, except that I've hidden a very subtle but important character. So we're replacing this empirical loss with a surrogate for the empirical loss, f hat, which is a upper bound defined by this here. So we're taking the average. Let me just go back so you can see this was the actual loss was with W here, and here now we are using the previous H's. And so why is it important? Recycling the previously found H factors, we're using them as approximate solutions of these subproblems. And so therefore, there's only a single optimization instead of having to solve all of these instances. So that's important. However, we may not have addressed the issue of having to store all of the history, right? We still are using all of these. But the good news is that just with a little bit of linear algebra, you can actually show that you can use these simple aggregate matrices to store the history, and you don't actually have to store all of the previous factors in memory. And so you just update these two aggregate matrices as you go, and that's all you need. So this really does fix the two problems. And in the tensor case, this also holds with a little bit more work in computing how the tensor aggregate look like. So I don't need to go into too much of the weeds here, but the good news is that their multiplicative update method is still quite practical, just like the original. Okay, so here is the method. Here are the three functions that we're using, and this is what they were able to prove, again, for the IID case. So they have an IID time series of data coming in with a common distribution pi, and they're computing these W and H factors using this Ontf method. Then they show that the empirical loss at time t, as well as its surrogate, actually do converge to the same constant, which suggests that the surrogate is the right thing to use, almost surely. And that we also get convergence at the gradient to 0, almost surely. So both of these are sort of the critical pieces. Of course, we're missing things like rates and things like this, which is something in the works. So what we wanted to do was to go beyond the IID case. So I'll just pause here for a second and mention why I think going beyond IID is important. So for obvious things, like if we're doing prediction of time series, for example, we looked at COVID data like many folks did, and to assume that COVID data is IID is probably a very bad assumption. And so we could that slightly and ask for a Markovian distribution, I think that's, again, maybe not completely practical, but at least a big step away from an IID assumption. And the other thing is if we're sampling large networks, then if we really wanted to sample IID, we have to be able to jump all over the network. And using a Markovian structure allows you to do a random walk, for example, across the network, which is a lot more practical in many settings. So several reasons why we think that the Markovian assumption would be a good generalization to make. So here's our result. We assume that we have an irreducible Markov chain on a finite state space, as I said before, with unique stationary distribution pi. And we let W and H T be a solution to the exact same algorithm. So I'll emphasize that we have not actually changed the method at all. We're just changing the assumption on how the data comes in. Then we're able to prove the following, same results, that an expectation, the empirical loss and the surrogate loss converge to the same finite limit. And in fact, again, they converge to the same almost surely as well. And we also get to the gradient converges to zero again, almost surely. So same outcomes with much more interesting, I would say, proof techniques, which of course I can refer to the paper for. So it was a non-trivial generalization, but I think it does actually at least help get us a little bit closer to what's actually done in practice. Okay, so I will transition to a bunch of applications. And again, feel free to interrupt if you want me to go back to anything. The first application I have is a project that we've worked with lymedisease.org, and they have an initiative called My Lyme Data. And they're collecting data from patient surveys who have been diagnosed with Lyme disease. So Lyme disease is a vector-borne disease typically transmitted by an insect or blood-to-blood contact. And symptoms often mimic those of others, such as MS, ALS, Parkinson's, fibromyalgia. And so it's hard to diagnose and they can become chronic. The CDC estimates 300,000 new diagnoses each year. And I think this has actually increased dramatically since I first wrote this talk. And it's also a grandiose underestimate because of the problem with diagnosis. So Lyme disease is a poorly understood, poorly funded, poorly diagnosed, and poorly treated disease, which the CEO of lymedisease.org said that's prime for using data to study it. And so that's what we were doing. So here's just an example. It launched in 2015. Now there's about 15,000 patients registered. The survey asks everything from demographic questions to questions about if the patient knows about a tick bite or an insect bite, diagnostic questions, how many doctors they had to see before they got diagnosed, many symptoms questions, which I'll focus on here, lab test results, questions about co-infections, which are very common, treatment questions, and quality of life. So it's a pretty extensive survey. And so here's just some examples of what you can do with NMF. I won't go into the details of what these three mean. I'll just focus on this rightmost plot here. So what we've done is we've taken data, which is symptoms by patients, and the patients are rating how bad their symptoms are for these various categories. And then we apply NMF and look at the topics and how the topics cluster. So there's several interesting things one can take away from this type of analysis. So I've just ordered these symptoms here to make it a little bit visually easier to read. So I've grouped the large values together. So you can see, for example, this first topic corresponding to this first column seems to group together nerve pain, psychiatric issues, muscle aches, and heart-related symptoms. So this is how we're reading this plot. Same thing with the second one is headache, joint pain, flu-like, and fatigue. So some interesting things. So we presented this and many other results at several board meetings for Lyme disease, and the physicians actually got really excited about some of these topics. For example, this third topic here, which corresponds to memory loss, twitching, sleep impairment, and cognitive impairment. This actually is very supportive of a conjecture from some clinical studies that Lyme disease actually has kind of many different realizations, and one of them is a neurologic realization. And so this tends to suggest that there are patients who very much are presenting with a neurologic version of Lyme disease, since these all correspond to Lyme. So it's not that the symptoms are just scattered among everyone. It really does seem that there are certain patients that just have these. So that was interesting. The other thing that they really found interesting was one of the few symptoms here that really doesn't fit in any topic is this bullseye rash. You can see all of it has very low values. And for many, many decades, physicians believed that the bullseye rash was the key to diagnosing Lyme disease. And now we're actually thinking that it's actually much less common than previously thought. In fact, we're now thinking about 30% of people or less actually present with a bullseye rash. And this is kind of suggestive of that it doesn't actually strongly appear anywhere. And so they got really interested in that as well. If we actually disaggregate the patients, so there's two groups of patients that take the survey. At the very beginning of the survey, it branches. And those are patients that consider themselves well, which is typically an in remission period, and patients that consider themselves unwell, so still sick, still being in treatment, and so on. And if we actually separate those patients who run the exact same NMF, we get very different topics, and that's very interesting to us. And in particular, this bullseye rash now in the well patients appears as its own topic. So evidence of a tick bite and bullseye rash are just dominant in its very own topic. And so this might suggest that the well patients presented with a bullseye rash, and that could suggest that they are diagnosed earlier, which could suggest why they ended up going into remission. So some interesting things there just on a very simple NMF. Leaving the medical world, we can do lots of things with text data as well. So this example is taking the book Adventures of Huckleberry Finn by Mark Twain, looking at the word adjacency matrix, which is here. So literally just whether two words are adjacent to each other or not, and how often that happens, gives us this matrix here. We can learn dictionary atoms by walking through that network, and we get these kind of structures here. And then we can do some reconstructions. And this might seem like, well, what's the point of this? But actually there's a lot of work being done that shows that you can do things like authorship. You can identify who the author is just based on the structure of the dictionary atoms. And so you can test for things like fraudulent authors and things like this. And in fact, one of my colleagues has gone a step further and actually shown that you don't even need the words, you can just use punctuation. And punctuation alone is actually enough to identify authorship. So it's kind of some interesting things that one could do there. So this was for ONMF by sampling the text. Other types of network applications, so quintessential social media network. We took the UCLA network as well as the Caltech Facebook network. And because we have results from our coding, we're sampling by doing a random walk across the network, and then we're learning the dictionaries. And the dictionaries for each of these networks are shown here and here. And just kind of looking at these qualitatively, you see that there are striking differences, right? So these UCLA ones are much sparser. They have kind of very distinct clicks in some of them, and otherwise are very empty. Whereas the Caltech one is very dense, right? All these atoms are very dense. And so that's not surprising if you know anything about Southern California universities. UCLA is a large university, very unlikely that people will know each other across campus, whereas Caltech is much smaller, and so you see much denser networks. So just ways to identify different structures within the network.
So there's a question, Deanna, about whether you use the reconstruction error on a new sample to rank how well it fits your learned dictionary for the fraud detection example, or a little bit more detail on how you would actually detect fraud, I guess.
Yeah, so I guess, one way would be to learn dictionary atoms for several different works by the same author. And then if you have a new text that you're checking to see if that author is the same author, you could use the previously learned dictionary atoms to reconstruct that new text. And if the error, like you said, is very bad, that might signal that you should look into that further. Or you can just qualitatively or even quantitatively compare the dictionary atoms, like in this case here, right? If I were to sample another network, I could probably detect which one it came from if I'm looking at UCLA versus Caltech. So similar there.
Yep, thanks.
There's lots that we can do with images as well. So here we again used Ontf. We did some random walks across the image and sample patches and learned dictionary atoms here, which again kind of look like the texture of the image, and use them for reconstruction. Again, you could do this for several reasons. Compression is one, although this may not be the best way to do this, but it gives you sort of an interpretable way of doing compression if you really want to learn the pieces that are used to reconstruct the image. Or we can do other things like denoising, or even color restoration is a new thing that we're trying. So here we took an original color image, learned dictionary atoms, and then took that same image and pretended that we didn't have color information. So we took the grayscale version and used these same learned atoms to reconstruct the image. And indeed, we got some decent color restoration. So we're at least able to sort of learn that grass is green and sand is beige. This was obviously an easier example because it was the same image. And so we're hoping we could do something more robust to actually do color restoration for new images as well. So that was just one direction looking at. We can do things like co-segmentation for images. So here we have images corresponding to several classes: cow, dog, car, and bicycle. The original image here is in the first row. We're using a semi-supervised NMF versus regular NMF. For this talk, it doesn't really matter the comparison, but we're now highlighting the topics that most correspond with the classification label. And so we're hoping that this would kind of segment the important piece of the image, right? So for example, the dog, the face seems to be the most important piece for classification. The bicycle is either the wheels or some case the handlebars. Video reconstruction, one can do, you can either treat the video as a tensor, of course you can unfold and do things there. You can do denoising to try to learn kind of the background from the foreground as distinct topics. This one is what I wanted to talk a little bit about, which is doing prediction. And so I mentioned this very briefly at the beginning, but what we're doing here is we have time series data. So this particular example is COVID data. And we're learning these dictionary encoding pairs as we sort of slide the window across, right? So this is X1, X2, X3. As I'm sliding the window, that's my new data point. And I'm learning these pairs. And I can do reconstruction and measure, right, the error at the current step. I can also do reconstruction where I've kind of slipped the window out into the future. So I have some data here, and I'm reconstructing the whole entire block, part of which I don't actually have any data for. And so this piece that I don't have data for, that I'm still doing reconstruction for, then becomes a prediction. And so we're able to do this and learn, kind of the hope is that you learn patterns that emerge that are sort of consistent, and you can detect those patterns. And so this is just an example of the actual dictionary atoms. We took these 6 countries as part of our time series. And then of course we have confirmed cases, recovered cases, and so on. And this is the shape, the different patterns that we see in our dictionary atoms. And then if we actually use those for prediction, as I said, by kind of slipping that window beyond the current time step, then we're able to get these results here. So this is for confirmed cases. Here's again our dictionary atoms. What I'm graphing here is the original actual data, which is the blue curve here, and then our prediction data, which is shown in red. And so this is for the 6 countries. And again, we're using all 6 as one set of time series data. So the hope is that they would correlate somehow with each other, which need not necessarily be the case. As you can see in many of these atoms, China, for example, has much different behavior. But nonetheless, we still get fairly good results. So these prediction lines line up actually really well just on local behaviors. You do see kind of some errors here happening. So for example, this was China data. There's this large spike in the actual data, and that really confused our algorithm, which is not surprising, right? Because if you see a large spike, you think something drastic is happening. And so you're going to predict something kind of wild. But in fact, everything kind of just went back to normal. So it could just be a data reporting issue that our method is not quite robust to. So as for confirmed cases, this is for deaths, kind of similar. For recovered cases, again, also kind of similar. Again, you see these spikes that really challenge us. But for many of it, it's quite interesting. So what I'd like to do in the future is combine this kind of local prediction with something more global, like using some SIR model in conjunction with this. So that will be maybe a future step.
Deanna, I have a question about your literary example. So in that example, do you use some sort of word embedding algorithm to represent the words? Is the dictionary learning part independent of the embedding of the words that you use?
Yeah, so for here, we actually did not use the word embedding at all. We just used the word adjacency matrix, but you can use word embeddings. There's semantic NMF where, remember when I had this semi-supervision term, or I had the labels, I had y minus like a times h, I forget what the variables were. Instead of having labels there, you can have some sort of word association matrix, and then you can like use that. So I can refer the paper to you after. I don't have it off the top of my head, but there is a couple of results that use word embeddings in that way. Now, the caveat will be that it's actually not like directly inputting the word embedding. There is just this word association matrix. So you have to sort of learn the word association matrix from the word embedding, which you can do in several ways. But yeah, there's definitely ways to incorporate that, but we did not do that in this case.
I see.
Yeah.
And there's also another question in the Q&A. So Daniel asked, by random walk in the image example, do you mean you sample image, the image in patches by walking randomly over it?
Yes, that's exactly what I mean.
Okay.
Yeah, so for the image case, whether I sample IAD or Markovian doesn't really matter. But we just did that since that was what the theory was for. But for other cases, it actually, I think, does matter. For the time series, it clearly matters. And for really large networks, it might be computationally easier.
Okay.
Okay, so here is just an example to the tensor case. In the tensor world, there's actually several things you can do, whether you unfold in certain modes. So here's a color image, right? So that's how we're viewing this as a tensor. And you can actually just treat the image as a tensor itself and do online tensor factorization, or you can do various types of unfolding across different modes. And long story short, in this quick picture is that you get, unsurprisingly, very different results depending on what type of structure you use. And so this is kind of something important to keep in mind if we're actually using color images like this. And it could be that the different factors that you learn based on the different unfoldings or treating it as a whole can actually inform one another. So it could be that they are complementary to each other. So I won't go into too much detail there. Here's another one that uses actually Ontf for EEG data. So this is studying node correlations from the UCI EEG alcoholism data. So they have 64 electrodes on patients who exhibit alcoholism, and they're trying to learn just correlations between the different nodes for various experiments. So this is probably not very meaningful, but here's some coloring of the nodes, and then these are actually dictionary atoms that we learned from that time series EEG data. But what might be interesting is how we actually can then use those results to predict correlations. So this is if you don't use any non-negative matrix factorization at all, you're simply just computing a Pearson correlation across the nodes. So you get this structure like this. And so blue values here mean that the two nodes corresponding to the row and the column are quite correlated with each other, so they fire together. And if we use ONMF, using those previous dictionary atoms, we actually can see some pretty maybe denoised correlations. We're not exactly clear. So it's quite interesting that you see kind of some similar structures here, like these large lines here, but they become very cleaned up. If we go a little bit further, we can not only use the actual time series, but the gradient of the time series, because we're interested in not only when things fire together, but also when the signal increases together or decreases together. So without going too much into the weeds, the point here is that it could be that treating these time series treating this data as time series and doing an MF to it actually might give us some interesting results. So again, here is the Pearson correlations with both the time series data as well as the gradient data. So you get a lot of interesting structure, and learning the dictionary atoms and doing reconstruction, we can predict the correlations actually look quite similar. So here, remember with the MF, you're picking the rank. And so I think this was like a rank 4, and then this is a rank 16. And the interesting thing, so the interesting thing is here we used ONMF with a time series as well as a gradient series data, so we just concatenated those. And here we actually didn't use the gradient at all. And the interesting thing we found is that we actually still get very similar results without actually considering the gradient itself. And this, of course, is a contrast to what we saw over here, where the Pearson correlations without the gradient looks much different than the Pearson coefficients with the gradient, but ONMF somehow doesn't need that gradient information. So I think the reason this is happening is because we're able to detect with these patterns, we're able to detect a lot more than just the actual data values. We're actually able to kind of pick up the gradient information for free, if you will. I have a couple more minutes. So this is Ontf again to learn activation patterns in a mouse cortex. So this is the image of a mouse brain. Pink and yellow values are areas of the brain that are very active while the mouse is being stimulated with certain things. So this is the spatial activation as well as the temporal activation over here. And so what this can do for us is when we learn like an atom like this, where it has very specialized locations of the brain, we can then jump over to that corresponding topic and see at what time, actually, I think if I count correctly, I think that's this atom here that I'm highlighting. And so you can see like it's this time step between maybe 1 second and 1.5 seconds. So then you can see what part of the experiment that was, and you kind of then can detect that whatever that the mouse was doing during that time, it was stimulating this part of the brain. So it's sort of an automated way of understanding when and why the brain areas are active. So I think I'll just wrap up to leave some minutes for questions, but we've done a similar prediction to learn weather patterns and predict weather behavior. As you can imagine, it's actually a lot smoother and prettier than COVID data. You have very natural, smooth patterns across days or years. So that was a nice example. My postdoc did some examples with physics, which I won't go into. But to summarize, some things that I think are interesting in open directions would be to do ONMF for a variable number of dictionaries. So right now we have like the dimension has been fixed over time, but it could be that as things get more and more complex, we might want to allow for a different number of dictionary atoms across time. ONMF for non-stationary data matrices. And then the question is, what do we want to learn in that case? It's not even clear, but that would be another kind of generalization of what we have. Dynamic topic modeling using ONMF is something that we've done. So in this case, we're not necessarily trying to learn the best dictionary coding pair and expectation, but we actually will allow the topics to change over time. And we like to detect when those changes occur, what topics are evolving, what topics are emerging and fading and so on. So that's kind of a natural direction. Extension to the online tensor factorization in terms of the theory. So there's not a convergence result known even for the IED case. And that's it. So thank you for listening and happy to take any questions.
Great, thanks a lot. Anybody who has questions, feel free to put them into the Q&A tool or chat, or if you have the ability, feel free to unmute yourself and ask them verbally as well. And Deanna, thank you for an excellent talk, of course. A round of virtual applause. Well, other people maybe collect their thoughts and think of something to ask. I guess in your list of things that you would think about in the future, you said proving a theoretical convergence guarantee for the tensor case. Yeah, exactly, which is what I was going to ask about. What is the main barrier to sort of carrying over the proof in the matrix case?
So there's a lot of random matrix theory that goes into the analysis. And because tensors just are so much more complicated, you lose, you know, even in SVD, right? For example, so we don't, all of those things just pretty much disappear when we go to tensors. The thing that does carry over, as I mentioned, is that those aggregate matrices, at least you can prove that they do actually carry the data. So the method itself still works, but to actually prove the convergence does not. So I don't think I answered your question, but
yeah, no, I think I
answered your question, but yeah, the answer is that the tools that are used in the proof just simply don't exist in the tensor world. So I think you just need a totally new approach.
Okay, all right. Mainly in the random matrix theory sort of side of things. It's interesting. All right, yep, let me see. It looks like there's a question in the Q&A here. I'll just read it off. So how would you extend this to the multi-dictionary case? Would it essentially be about merging several optimization functions for from the single dictionary case? Is a question from Daniel.
I guess I'm not sure what is meant by multiple dictionaries. Is it this variable number of? So here what I meant was that the actual rank could change. And so can we detect, so there's ad hoc ways you can detect whether you need to change the rank, right? If you're so there you could just compute the error, the loss function value, right? And if that is getting too large, then you might want to update the rank, increase the rank. If that was the question, that's what I meant here. It was just allowing for different sizes.
So Daniel, I've given you permission to talk if you want to follow up and on your question. Or not, it's also okay. Okay, yeah. All right, so any other questions, or if Daniel, if you want to follow up that people might have.
Hi, Deanna, I have a question. This is Mike. Hi, I was wondering, after you've worked on all these different types of data, does that inspire you to think of any other types of structure in these non-negative factors that you think would be useful, kind of beyond sparsity?
Yes, that's a great question. We've done some work with incomplete data. So that's something I've been thinking a little bit about. And so, right, typically you can do like matrix completion or something like this, and you assume just low rank. But I think in a lot of these cases, if you don't see all of the data, there could be a reason that you're not seeing all of the data. For example, in movie ratings, if I don't rate a movie, it could be more likely because I don't want to watch the movie. And so it could be that rating is low. So I don't know if there's something like that we could do here, right? Or in the incomplete data case, that's sort of a natural thing to do. Other structures, like maybe in networks, that could be something similar as well. If you're not traversing part of the graph, it could be because that part of the graph is actually not connected very well, and things like this. But yeah, I guess the other thing is like the COVID data, for example, we're completely ignoring all of like science and epidemiology, right? We're not trying to use a model or anything. And I think that's a big place where we can improve quite a lot. So we're just, kind of blindly learning patterns and making predictions from those patterns. We have no awareness that there is like many models that can do more global scale prediction. So I think that would be something I'd really like to incorporate into these methods, is to have some sort of prior, if you will, on how the data is expected to behave, and then use like local information to sort of booster that.
Someone is at the front door.
Interesting.
My front door now.
Thank you for the nice talk.
But yeah, I think that's a really interesting question. And yeah, depending on the data, if there be other things we could use that's more informational. If you have any thoughts, definitely let me know.
Any other questions out there that folks might have? Feel free to chime in. Otherwise, I guess we can thank Deanna one more time for a great talk, and see you guys back here next week.
Thank
So
you,
thanks.
everyone.